All right, so now we're going to go to polar area. And we have a funky formula here, 1/2 integral of r squared d theta, where they're given an r, which is a polar equation. So conceptually speaking, here's what's happening. We have a circle, and let's see, we have a quadrant or a sector of the circle carved out by theta. And this, of course, is the radius. Now we know that the area of a circle, of the entire circle, is pi r squared. And we know that this region of the circle is some portion of the entirety of the circle. So theta is some portion of 2 pi, which is the angle around the entire circle. So what ends up happening is that the portion that is this sector's area is going to be pi r squared times the proportion of the circle covered by this sector of the circle. And when I simplify that, the pi's go away, and I'm left with 1/2 r squared times theta. Now in calculus, as you know, we don't deal in large quantities of theta, we deal in tiny little slivers. And so our sector might just be this big, and that angle measure, instead of calling it theta, we're going to call it d theta for a tiny change in theta. So that brings us to 1/2 r squared d theta, which is the polar area. And of course, then we have to integrate that from A to B, taking tiny little slivers of theta as we go. So if this is our R value, in order to get the polar area, we take 1/2 integral from, actually it'll be 0 to 2 pi because we're going one full revolution. And then we have r squared, which is 2 plus 2 cosine theta, d theta. We're going to put that, squared, 2 plus 2 cosine all squared d theta. We put that into our calculator and we find out that the area is 6 pi. And now is a good time to mention that not all the time are our limits of integration 0 to 2 pi. They're either going to have to tell you that the limits of integration are different, or they're going to have to give you a calculator in which you'd figure out what the limits of integration for. And we will encounter problems like this as we go, and sort of will discover them as we go. But polar area, you're just going to memorize as 1/2 integral of r squared d theta. So this question says, find the area that lies inside the circle and outside the cardioid. So it's best to use your calculator to assist you in graphing these. A circle with a sign means it's centered up here on the y-axis, and the 3 is actually the diameter. So this circle is going to look like this. And again, you can use your calculator in polar mode to graph these. This is a cardioid. This r equals 1 plus sine theta is a cardioid that looks like this. Actually, I'll do it in a different color. Looks like this. So they want us to be inside the circle and outside the cardioid. So it's this region that I'm putting in black stripes right there. So what I want to do is I need 1/2 r squared d theta. But in this case, I have a big R squared minus a little r squared. So the big R squared is this circle. So 3 sine theta squared. And the little r squared will be the cardioid. We're going to subtract out this portion. So 1 plus sine theta all squared. Don't forget your d theta at the end. So we have big R squared minus little r squared. We just need our limits of integration. Well, they come from the intersection points between the two curves. And basically what you're doing is you're taking a radius, starting at the pole, and going through each of the limits of integration. And these are the intersection points. And so what you're doing is you're sweeping an angle from this angle all the way over to this angle. And you're sweeping the area that is outside the cardioid but inside the circle. So we're no longer integrating with respect to x or with respect to y, but now we're integrating with respect to the angle that sweeps through our area here. So we need to know these intersection angles. The way to do that is to take our two r values, 3 sine theta and 1 plus sine theta, and set them equal to each other. If I subtract sine from both sides, I get 2 sine theta equals 1. Sine theta is 1/2. And there are two places on the unit circle where sine is a positive 1/2, and they are at pi over 6 and 5 pi over 6, which visually makes sense. Here and here look to be about pi over 6 and 5 pi over 6 on the unit circle. So now you're going to put this in your calculator and evaluate, and you will find out that this area that we're looking for is pi. Last one, they want to know the length of the cardioid. So this is an arc length problem. So this cardioid we just looked at a minute ago, this cardioid looks like this. So to get the full length, we need to go from 0 to 2 pi. So 0 to 2 pi. And then, of course, for arc length, we need dx d theta squared plus dy d theta squared, all square rooted, and times d theta. Well, to get dx d theta and dy d theta, we first have to get x and y. So, of course, x equals r cosine theta, so 1 plus sine theta cosine theta, and y equals r, which is 1 plus sine theta times sine theta. And when I differentiate these, I need the product rule. I'm going to get that dx d theta is equal to, let's see, sine goes to cosine times cosine, so that's cosine squared, plus 1 plus sine theta times the derivative of cosine, which is negative sine. So that will be my dx d theta. My dy d theta is going to be the derivative of 1 plus sine theta, which is cosine theta, times sine theta, plus 1 plus sine theta times the derivative of sine, which is cosine. So these are both quite long. I hope you don't mind that I don't try to fit them in underneath here. Just know that you need dx d theta squared and you need dy d theta squared. Again, these are calculator problems, so you're going to plug in all of this into your calculator and you're going to evaluate the integral from 0 to 2 pi. Please check it and make sure that you get 8. A very common mistake is that people forget the radical sign in here. So if you're trying this in your calculator, which you should be doing, make sure that you're getting 8 out.